Greetings. We're going to continue our discussion of perceptrons that we started in our last video. Perceptrons, and let me make my pen a little bit thinner. There we go. And remember that the perceptron was a single processing unit like this, and there were several inputs depending upon how many attributes we were checking. So in this case over here, there were 4 attributes, and there is a single output over here, like that. And we are going to assume that there are these weights here, W1, W2, W3, W4. And again, we have some observed data. So we're going to assume that there is attribute 1, and there's attribute 2, and there's attribute 3, and there's attribute 4. Okay, and those are the input things. And then there's some variable that we're trying to predict. So I'm going to come over here and call this the predictor. And we have some values over here. These are real numbers. And the predictor is either yes or no. In other words, either this is a good student or it isn't a good student. And we have some other value over here. And maybe this is no. And we have a whole bunch of these in here. And this is what's referred to as our training data. And remember, what we do is we make some initial guesses over here on these weights here. And we take a particular exemplar here and we put it on. So I'm going to call this X11. And I'm going to call that 1-2, 1-3, and 1-4. And we would come along over here and we would put each one of these on the network and see how it computes. So we would look at X11 and we would multiply that times W1. And then we would go plus X12 times W2 plus X13 times W3 plus X14 times W4, and then there is this thing called this threshold, and we would ask if this thing is greater than or equal to the threshold. And if it is greater than or equal to the threshold, we would output a 1. And we're going to do something a little bit different here. If it turns out that it is less than t, we're going to output a -1. Remember last time what we had is we had binary output. Now we're going to make it bipolar output. It turns out that the two models are completely equivalent, but it's computationally easier to talk about bipolar. So we will assume that a 1 means yes, and we will assume that a -1 means no. Okay, and remember the way that this works is we put a particular example on the network, and we see if it outputs a 1 or a -1, and then we see if that agrees with the predicted value. If it agrees with the predicted value, we don't do anything to the weights or the threshold. If it doesn't agree with the predicted value, then what we're going to do is we're going to adjust all of the weights, and we would go ahead and also adjust the threshold, and we'd move on to the next example. And we repeat this iteratively, and our goal is we want to make it through all of our observed data and correctly predict the column over here. Once that is done, we have these values W1, W2, W3, W4, and the threshold, and we would say that the network is trained. Okay, it has learned. And now what we can do is we can use this network, this perceptron, to go ahead and make predictions about data that we haven't observed, like this over here. Now, in this video, this is not going to be a particularly long video, but there are a couple of mathematical things that we want to talk about. And what we want to do is we want to simplify our model a little bit. So I want you to look at this equation over here, and I want you to note that this is actually the equivalent of saying X11 W1 plus X12 W2 plus X13 W3 plus X14 W4 plus -1 times t. and that's greater than or equal to 0. Okay? So in other words, what I've done over here is just take this equation right here and subtract t from both sides, and you end up with this expression right over here. Well, that's almost like making this another attribute, okay? In other words, we could, if we wanted to, we could call this x15, and we could come over here and we could just call that another weight if I wanted to. I could call it w5. Actually, what we like to do is we actually, instead of doing it up here, we like to stick it at this end, and we would actually call this x10, and we would call this w sub 0. Okay? But then, what that has done for us now, let's come over here, and I need some more space. So now what happens is instead of having, I'm going to call it attribute 1 and attribute 2, attribute 3, attribute 4, and here's prediction. We come over here and we would have attribute 0. And again, let's just go back and look at what we said last time. What we're going to do is we're always going to make our attribute 0 just minus 1. So this would be minus 1. And then we would have whatever value we had before and the same predicted value as before. So for this one, we would make this a yes. So this would be x 1 1, 1 2, 1 3, 1 4. And again, we'd come over here. Here's a minus 1. And now I would have, say, x21, x22, x23, x24. And in that particular example there, we said that's a no. Okay? And so what's happened here now is we would just say, well, for this one over here, this is always going to have the value minus 1. And our threshold is just another weight. Okay? And in a moment, we will give a geometric interpretation of that. Okay? So that's the first thing that I want you to take note of. Now here's the second thing I want you to take note of. We're looking at things that look like this. We're looking at things that go like x0, w0, plus x1, w1, plus, and we're going up to some, say, x sub n, w sub n, and we're asking if that's greater than or equal to 0. Okay? So in here, you might be confused because here they have 2 subscripts, over here they have 1. In other words, what I'm trying to emphasize here is that I've got n plus 1 weights, w0 through wn, and I have these input values here, and I'm multiplying like this to see if it's greater than or equal to 0. And the question I have is, what is this? Okay, what does this thing look like? And you might have trouble thinking about it with so many variables. So what I want to do is consider something simple. Suppose I just had something like this. Suppose I were to say to you x0, w0 plus x1, w1 is greater than or equal to 0. Well, this doesn't look so bad. Remember, what we're looking for here is we have a table over here of some attribute 1, and we have some attribute 2, and remember we have this attribute 0 now. Okay, actually in this case, it's only this case right here. These are all minus 1s, and these have some other numbers in them, like that. What we're trying to do is and then there's the predicted value over here. So there's predict. And we're trying to find w0 and w1 so that when I put all of these values in this table on here, it correctly predicts the output. In other words, for all of the ones here that say yes, it's going to be greater than or equal to 0. And for all the ones where it says no, it's going to be less than 0. Well, again, you may look at this and go, I don't quite get what that is. But let's think about this a little bit more. Suppose that the network has been trained. Well, that means that these two things over here have some numbers. So maybe W0 equals 3 and W1 equals 2. All right, what does this thing look like now? Well, now this thing looks like 3x0 plus 2x1 is greater than or equal to 0. Well, maybe this still bothers you, but I'm going to change the names of the variables. Suppose I were to say to you 3x plus 2y is greater than or equal to 0. And now you go, oh, wait a second. I recognize this. We learned about things like that in algebra. And that's exactly the point that we're getting at here. Okay? You could come over here and I hope that you remember that something like this is going to be the equation of a line. Okay? In fact, you might remember what I might do is I might say here that 2y is greater than or equal to minus 3x. And then I might divide things and I might say y is greater than or equal to minus 3 over 2x. So we recognize that this is a line that goes through the origin, like that. And let's see, we're looking at a line that has a slope of minus 3 over 2. So it's the change in y over the change in x. So if I come over here, 3, this, whoops, change in y would be minus 3. I'm sorry. Change in y would be minus 3, right there. And the change in x would be 2. So we would come right over here, and there's a point there. And again, you can see if I go 2 here, I would come up and go 1, 2, 3, and it would be this point right over here. And we can see that the set of x and y's that satisfy this, I'm going to come over here, and I can't draw very straight lines, but I think you all get the idea. And then it's determining one of these two sides of the plane. I don't know which one it is. Well, what if I come over here and I put 1, 1 in here? Does 1, 1 work? Yeah. If I put a 1 in here and I put a 1 in here, that's 3 plus 2 is 5. So this would be a positive example right over here. Okay? And I think you could see that all of these over here would be positive examples as well. So this is the positive side, and this is the negative side. And you recognize here that if I have two attributes, okay, and I'm trying to solve something with a perceptron, what I'm basically asking for is there a line that I can draw in the plane that puts all the positive ones on one side of the line and it puts all the negative ones on the other side of the line? And this has a very famous name. This is what's called linearly separable. And what this means, this is a very big theoretical result when it comes to the perceptron. The perceptron can only learn examples that are linearly separable. Okay? Let's consider an example over here. Let me show you something interesting. Suppose I were to come over here, and suppose I were to talk about A, B, A, and B. Okay, now I'm talking about logical A's and B's, and we could come over here, and if we wanted to assume, for example, bipolar input, okay, and we're assuming 1 means true and minus 1 means false. If I'm talking about A and B, we know that this is the only true one and these are false. So if I come over here, we know the following. If I come over here to 1, 1, over here, there's a positive example. If I come over here, there's a negative example. If I come over here, there's a negative example. And if I come over here, there's a negative example. So the question I have, looking at these 4 points right over here, the question is can I draw a straight line that puts all the positive examples on one side and all the negative ones on the other? And the answer is sure. I can actually draw a lot of different lines, and here's one right there, just like that. Well, what does that mean? It means that I can learn this, and I'll put this in quotes. I can learn this with a perceptron. I know we haven't talked about the learning algorithm yet, and we will get to that shortly, not in this video. But I want you to appreciate that what this means is that this is learnable. Now, I think you would also verify, I leave it to you, that A or B is also learnable. But now here's the big result. What happens if I come over here and I talk about A, B, and maybe you remember this thing over here, A exclusive OR. Okay, so I have -1, -1, -1, -1, 1, 1, -1, and 1, 1. Well, remember, exclusive OR is only true when one is true and one is false. So this would be 1, and this would be 1. This would be -1, and this one would be -1. If I come over here and I draw the pictures of these, you can see that it is going to be true here, and it's going to be true here, but it's going to be false there, and it's going to be false there. And the question is can I draw a line that puts all of the positive examples on one side and puts all of the negative examples on the other? And the answer is no, I can't do that. And that has a very profound theoretical result. It means that if I were to use a perceptron with this input data, it's not going to converge. Okay? It can't learn this particular function. Okay? Now, things get more complicated in higher dimensions, and I am not a very good artist here, but what's going on, suppose we had 3 attributes. So we have input vectors that look like this. Like we have x11, or I'm sorry, x01, again, I'm making mistakes here, x10, we have x11, and we have x12. And again, we're multiplying this times some w0, w1 plus w2, and we want to know if that's greater than or equal to 0. Well, what's going on here now is now we're dealing in 3 dimensions, something I don't draw very well. But it might look something like this. And remember, what's going on here is we have a bunch of observed data. We have different values for these x's, and we want to, and they're labeled, meaning that the output indicates that they're either yes or no, or true or false, or 1 and -1. And what the geometry of this means is it means, can I draw a plane? And again, you'll have to pardon my artistry here. So there's a plane there in 3 space, okay? And I know this is a terrible drawing, but there are points above this plane and there are points below this plane. And the idea is that we're somehow able to put all of the positive examples on one side of the plane, and we can put all the negative examples on the other side of the plane. We would then say that the data we have is linearly separable, and we could solve this with a perceptron that has 3 inputs and 1 output. We can extend this up to 4 dimensions, 5 dimensions, 6 dimensions, 20 dimensions, okay, no matter how many attributes we have, okay? The question becomes, is the data linearly separable? So in other words, if we have n input attributes, okay, which means they basically go from attribute 0 all the way up to attribute n minus 1. Remember, if we start them at 0, it's going to go, n of them would take us all the way up to n minus 1. And remember, this one over here, we've decided is, we say that this is clamped at minus 1. Okay, that actually corresponds to our threshold. Okay, so the question is, can we find the hyperplane that separates positive from negative examples? Okay. Hello again, restarting the video, and I just want to talk about some mathematical notation here. Okay, so this has to do with linear algebra, and I am assuming that the folks that are listening to this talk haven't had any linear algebra, but we can still borrow some notation from linear algebra. And in linear algebra, a lot of times we talk about things called vectors. Okay, and here we are in 2 space, and if I come over here to the point, I don't know, this is 1, 2, 3, 1, 2. So this is the point 2, 3. Now that's the point 2, 3, but here is what's called the vector 2, 3. It starts at the origin and it goes that way. So a lot of times in this situation over here, you'll see people will say, oh, the vector v is equal to the ordered pair 2, 3. And you'll hear people talk about the dimensionality of vectors. So the dimension of this vector v is equal to 2. There are 2 components over here, just like that. Okay? And when we're talking about vectors, we put this little arrow on top of it to mean that we talk about vectors. And you can do all sorts of wonderful things with vectors. Like if I have another vector here, w, and let's suppose w is equal to 5, 1. You can talk about v plus w, and the way that you add the vectors is actually very simple. V plus w would be 2 plus 5, and then it would be 3 plus 1. In other words, I'm adding each one of the components together, and that's equal to 7, 4. Nothing very fancy about that. But here's what I want to talk about here. There is an operation that's referred to as the dot product. It goes by another name. It's also called the scalar product. And it says the following: if I have 2 vectors of the same dimension, and I'm going to make a couple up here just for an example. So suppose I have u, and it's a vector, and it's equal to 3, 1, 4. And I have another vector here called v, and that's equal to 5, minus 2, 1. I can do this thing called the dot product, and I write it this way. It's u dot v, and it's equal to, well, I'm going to multiply the 3 times the 5, and to that I'm going to add the 1 times minus 2, and to that I'm going to add 4 times 1, and that's equal to 15, and that's going to be minus 2 plus 4, and that's equal to 17. Okay? So the question is why did I bring this up? And I think you can see why I brought it up. When we're talking about a neural network, and we have some network over here that looks like this, and we're going all the way from W0 up to some W sub n minus 1. And over here we might have some attribute 0 all the way up to some attribute n minus 1. And we have some prediction over here. And this might correspond to x1, 0 all the way up to x1 n minus 1. And I don't know, maybe this is yes. And over here I've got x2, 0, and this goes all the way up to x2 n minus 1, and that's a no, and this goes all the way down like that. Okay, and what I want to do over here is I'm going to call this x1, and what I'm going to do over here is I'm going to call this x2, x3. So in other words, I could come over here, and if one way I could describe vector x3 is it's equal to this tuple. It would be x3, 0, x3, 1, all the way up to x3 n minus 1. Okay. Likewise, we come over here when we talk about the weights that are over here. We can have a what's called a weight vector, and that's equal to W0, W1, all the way up to W sub n minus 1. And we can see that what we've done here is we can rewrite the perceptron problem here very simple. We could just say is x3 dot w, is that greater than or equal to 0? If it is, then the predicted value should be yes, and if it isn't, the predicted value should be no. This notation over here is very, very, very convenient. And here's a little homework for you. Show that if x dot w is actually equal to 0, then x and w are perpendicular. Okay? What you might want to do just to see this is try it in 2 dimensions, make some examples up, try it in 3 dimensions, and make some examples up. Okay? Again, this is a notation that is very, very convenient. Okay, I think that's the end of this tape right here.